Now this is just a continuation of where we left off because the last video got disrupted a little bit. So we left off with that gastroesophageal sphincter, which are also known as the lower esophageal sphincter. So we looked at the histology of the neurological histology of the esophagus. So now let's work our way in here. If you look here, we talked about the type of tissue that exists, whether it's skeletal or smooth muscle. Well, first of all, here we are in the esophagus, right down here, about midway, right? And we notice up here, the esophagus-stomach junction is here. This here is going to be located right here. Now, at this place up in here is mostly skeletal muscle. You can voluntarily swallow food. But as you get food down a ways into the esophagus, there's a combination of voluntary movement and autonomic contraction to push it down there. So if you look at the skeletal muscle, which we know, and the smooth muscle, it's a mixture of both. And which is interesting here, if we look here, remember we had our mucosa, here's our lumen, the opening right there. There's the mucosa, which is stratified squamous epithelium, which would be right about in here. And then we have our submucosa, which we saw before. We looked at the histology of the alimentary canal, then the muscularis externa. The muscularis externa has a combination of skeletal muscle and smooth muscle. This is going to respond to voluntary movement. You're going to control the swallowing. This part here is going to respond to the myenteric plexus built in to the muscularis externa, okay? This part responds to stretching of the esophagus as the bolus of food moves down. Now, when you get down here, farther down here, to the lower esophagus where the esophageal, gastroesophageal sphincter is, you're going to notice that we switch over. The esophagus is here. The stomach junction's right there. Okay, that's the junction between the esophagus and the stomach. Well, the stomach's epithelium is simple columnar, where this was stratified squamous. And the reason is this is exposed to more abrasive force, so it's stratified squamous. This here is going to have more of a secretory function, which we'll talk about later. That's why this epithelium here becomes columnar, simple columnar. Okay, again though, the main thing here is at the midpoint, there's combinations, it's a combination of skeletal. Up here, it's skeletal, voluntary movement. Here's a combination of skeletal and smooth. Here it's smooth. Okay, there. Now, swallowing, okay, the phases of swallowing. If you notice here, that you have to push that bolus of food back with the tongue. It's been chewed up, salivary glands have exposed their chemicals and mucus. The bolus of food's pushed back here to the oral pharynx. But look at, we have a nasal pharynx up here. If you push this food up this way, it would go out the nose. Okay, so we have a soft palate here, which we're going to see in a second. It's going to block this when you swallow. The oral pharynx is the part that's back behind the mouth. Okay, this is the upper esophageal sphincter. That is closed, okay? It's closed. You have an epiglottis, which blocks the trachea. Now, this is the voluntary phase. You're voluntarily pushing the food back to the oral pharynx, okay? Now, here in the pharyngeal phase, because it's back in the pharynx, the soft palate seals off the nasal pharynx right here. You don't want food coming up into the respiratory area, right? So the soft palate right here blocks the nasal pharynx. The epiglottis here seals off the larynx, which is the opening to the trachea. You don't want food going down into the trachea or windpipe, okay? And then the soft palate, okay, seal it off. And everything is sealed here. The soft palate seals off the nasal pharynx. The epiglottis seals off the larynx. Then you have the esophageal phase, okay? Open upper esophageal sphincter, so that opens up here. The peristaltic wave is, again, it's skeletal muscle. It's kind of you swallow and the food moves down into the upper esophagus. Okay, so again, the main thing here with swallowing is in the volunteer phase, we have the bolus of food, you push it back to the back of the mouth, the oral pharynx. Okay, but before you start that swallowing, or when you start to swallow, the pharyngeal phase, because it's in the pharynx here, the soft palate blocks off the nasopharynx and the epiglottis blocks off the larynx. And then you have the esophageal phase where the upper esophageal sphincter is opened up, okay, and food can move down into the esophagus, swallowing, okay? Now let's take a look at the stomach here a second. In the stomach, first of all, if we notice here, we have the diaphragm, which is the muscle, the respiratory muscle that actually runs just below your ribs, right here, okay? And you'll notice there's what they call a hiatus here, and a hiatus is just an opening. So the esophagus goes through the diaphragm, the hiatus of the diaphragm, and actually connects to the fundus of the stomach. Now, there's the lower esophageal sphincter right here, which controls the food leaving the esophagus to the stomach. Now, the stomach's parts, we have the cardiac or cardia part, which is closest to the heart. This is the cardia part of the stomach. This is the fundus part of the stomach. This is the body of the stomach. And then you get down here and you have what they call the pyloric antrum. And then the pylorus region, and then the pyloric sphincter. Okay, so again, the diaphragm, the hiatus of the diaphragm, or the opening of the diaphragm, the lower esophageal sphincter, the fundus of the stomach is right here, this dome-shaped region of the stomach, that's the fundus. This over here is the cardia part of the stomach, and then the big rest of the stomach is the body. And then you get down in here and you have the pyloric antrum, this region right here. Then you have the pylorus, which is this region right here. And then you have the pyloric sphincter, which is the muscle that controls the movement of food from the stomach to the duodenum. Now, if you notice here, the muscularis externa, remember, we have the muscularis externa, the submucosa and the mucosa. The muscularis externa of the stomach has the outer longitudinal layer, a middle circular layer, and an inner oblique layer. So it actually has three different dimensions that allows it to churn the food up. Outer longitudinal, middle circular, and inner oblique. Okay, and this rough stuff here is called the rugae. And this is stuff that actually allows the stomach to expand when it stretches. Okay, there. And we already said before, this is the lesser curvature, and that's the lesser omentum. And this is the greater curvature of the stomach, and that's the greater omentum. So that's the parts of the stomach. Okay. Okay, let's take a look at the stomach mucosa. Remember again, I guess the histology. We have the muscularis externa. Remember the serosa was the visceral peritoneum. Then we have the muscularis externa. In this case, for the stomach, we had three different layers, right? We had oblique, circular, and longitudinal. Then you have your submucosa. And remember, the muscularis externa had a myenteric plexus, the enteric nervous system. The submucosa had a submucosal plexus, and then the mucosa is the part that's the next one before you get to the lumen of the stomach, or the opening of the stomach. Now in the mucosa, we had the lamina propria, we had the muscularis mucosa that's in the mucosal layer. And then you had, actually had the muscularis mucosa, then you had the lamina propria, then you have the epithelium. And the epithelium in the stomach has what they have these gastric, remember it's columnar epithelium. We have gastric glands and gastric pits. Okay, in the mucosa, gastric glands, that region right there is the gastric gland, and that's the gastric pit. You have to get a vision behind that. Now, if you look at the gastric glands, let's go back here a second. They're found at the base of the gastric pits. They secrete hormones and other stuff. Let's take a look at a better image of this right here. I want you to see this here. Now here is our gastric gland. We were just pushing up before. And here's the gastric pit. Now the gastric gland contains the enteroendocrine cells. These are enteroendocrine cells. Now entero means within. Endocrine means it's going to secrete something into the bloodstream. And then you have the parietal cells and the chief cells. These are all part of the gastric gland. So the enteroendocrine cells, the parietal cells, and the chief cells. Now up into the gastric pit, which is a little farther up here, we have the mucous neck cells. Remember, this is a columnar epithelial cell, simple columnar epithelium. It contains goblet cells. This is the gastric pit. Basically, it's made up of simple columnar epithelium. It contains mucous neck cells and goblet cells. Okay, so we have gastric gland. The gastric gland has the enteroendocrine cells, the parietal cells, and the chief cells. The gastric pit contains the mucous neck cells, the goblet cells, and they're basically simple columnar epithelium. This right here is your simple columnar epithelium. They're secretory in function. Now, let's take a look at this here a second, how these work together. Okay, make an overall picture here. Here's the response in the stomach, a digestive response. First of all, if you want to increase the acidity or activate the digestive enzyme within the stomach lining, the first thing is you have a stimulus. We'll talk about that in a second. But when the stimulus is activated, the enteroendocrine cells, also called G cells, because they release gastrin. Gastrin is released by the enteroendocrine cells into the bloodstream in the submucosa. They travel up along that submucosal region, the blood vessels, and they actually cause the parietal cells to the sodium potassium pumps in the parietal cells to activate. They actually activate ATP. ATP opens the sodium potassium pump. Potassium can rush in, okay, change the membrane potential. In response, hydrogen is released by the parietal cells. As hydrogen released, because it's a positive charge, the chlorine ion will follow. Now, in this lumen area of the gastric gland, we're going to have hydrogen ions and chloride ions together will form hydrochloric acid. So parietal cells eventually make hydrochloric acid. Now the chief cells secrete pepsinogen. Anything that's an inogen is what they call an inactive zymogen. Pepsinogen is inactive, but when it's released into this lumen of the gastric gland, the hydrochloric acid activates or converts pepsinogen to pepsin. Pepsin is the digestive enzyme for proteins in the stomach, okay? Now let's take a look at this again. A stimulus occurs, we'll talk about that in a second. It causes the enteroendocrine cells to release gastrin into the bloodstream of the submucosa. The gastrin activates the parietal cells, the sodium potassium pump in the parietal cells, and causes the it causes the cells to release hydrogen into the lumen of the gastric gland. Chlorine follows the hydrogen being negative charge. This forms hydrochloric acid. the chief cells secrete pepsinogen, which is the inactive form of pepsin. Hydrochloric acid will convert pepsinogen to pepsin, and pepsin is a digestive enzyme for proteins. Okay? Let's look at the phases here. If we look at these phases, we'll get a better understanding of what's going to cause these secretions. First of all, it's called the cephalic phase. Now, which means it's the brain phase, okay, cephalic phase. There is some type of stimulus that activates the smell, thought, taste of food, sight of food. This stimulates the vagus nerve in the central nervous system. The vagus nerve is a parasympathetic nerve. This nerve is one of the long reflexes that actually goes all the way down into the stomach to the parietal cells. And, well, actually this whole region, the gastric glands, it activates the gastric gland. The vagus nerve causes the gastric enteroendocrine cells to release gastrin. So we have an increase in gastrin. Also, it causes an increase in the release of histamine. Now, for those of you who have had allergic reactions, histamine is going to cause the production of mucus, right? Because you get congestion and stuff like that. And you have a decrease in somatostatin. Now, the increase in gastrin, the increase of histamine, and the decrease in somatostatin causes a release of the hydrogen ions by the parietal cells. Now, when it's going to happen, the hydrogen ions are going to convert to hydrochloric acid, and then the chief cells that release the pepsinogen are converted to pepsin by the hydrochloric acid. So now we've changed the acidity. We've activated pepsinogen to pepsin. So now anytime a protein enters that stomach area, it can be broken down in that chyme. That's a cephalic phase. Again, thought, sight, smell activates the vagus nerve in the central nervous system. The vagus nerve on its long reflex down to the stomach area activates the enteroendocrine cells to release gastrin. You also have a release of histamine, and you have a decrease in somatostatin. This in turn causes the parietal cells to release more hydrogen, creating more hydrochloric acid production in the gastric glands, which in turn converts the pepsinogen from the chief cells into pepsin, and you can digest protein. That's a cephalic phase, okay? Now the gastric phase. In the gastric phase, this is going to take place in the stomach, okay? So the food enters the stomach. You're going to get a little stretch reflex there, but still we have the vagus nerve activated because it already has a thought, smell, all that part of the stimulus in the central nervous system. But when you have kind of the stretch of the stomach, the food, then we have the enteric nervous system in the stomach activated. Remember, in the muscularis externa, we had the myenteric plexus. In the submucosa, we had the submucosa plexus. Both of those are enteric nervous systems. They're going to be activated. Now, these both this the long reflex and the short reflex, both the vagus nerve and the enteric system are going to activate the gastric enteroendocrine cells in the gastric glands to produce more gastrin and more histamine and less somatostatin. We already know that gastrin is going to affect the parietal cells to produce hydrochloric acid, but you can convert chief cells, pepsinogen into pepsin, and you can digest protein. Okay, now there's a positive feedback here, and as the more partially digested food there is in the stomach, the more gastrin is going to be produced. This is going to be part of that enteroendocrine cells in response to this partially digest. Because if there's partially digested protein, we want to continue to digest it. That is what they call the intestinal or gastric phase. Excuse me, gastric phase. The intestinal phase. Let's get all the way back here. We'll look at the intestinal phase. See, we have partially digested protein entering the duodenum. Now, the duodenum is the part of the small intestine where, remember, the stomach had that pyloric sphincter, and then the pyloric sphincter opens into the duodenum. So if there's partially digested proteins entering the duodenum, we don't want that. This stimulates the vagus nerve stimulation, and it causes all this stuff to continue. intestinal gastrin in this case. So again, we're going to have, even the small intestine doesn't do a lot of digestion of protein, but it does do some. Now, when you produce intestinal gastrin, you increase hydrogen ion concentration, which causes the pH to decline or get more acidic. And the presence of lipids in the duodenum, both declining pH and the presence of lipids in the duodenum, are going to affect the enterogastric reflex, which is going to stimulate the vagus nerve activity and hydrogen ion secretion. We're going to produce more secretin, more gastric inhibitory peptide, and we produce more hydrogen. So again, we're going to produce more pepsin to break down protein. So in the declining pH and the presence of lipids in the duodenum, you're going to set off all this enterogastric reflex, the vagus nerve, increased secretin, gastric inhibitory peptide, and you produce more acid, and you make more pepsin, and you digest more protein. This is what they call the intestinal phase. Now, if you go back here, these are ways, if you think about these here, well, first of all, hiatal hernia, GERD, gastroesophageal reflux dystrophy. This means that you're going to get reflux from the stomach, the gastro, back into the esophagus. Okay, it's due to the sphincter, the lower esophageal sphincter not being able to contain the food as the stomach contracts. It will push some of that reflux back up into the esophagus. This is not good because the esophagus is not designed for that kind of an acidic environment. You're going to create problems. And some of the problems can deal with your vocal cords, esophageal cancer, respiratory problems. You do not want to regurgitate gastric contents back up into the esophagus normally. Now, hiatal hernia, hernia means the tearing. So if that hiatus is torn, then in that diaphragm, in that stomach, and the sphincter can move up above the diaphragm, making it easier to reflux the contents of the stomach into the esophagus. Not a good thing. Now, how do you treat it? Well, there's indication there may be contributed by a bacteria that causes chronic inflammation in that region. But here, it can be dietary modification, less caffeine. Well, caffeine is somewhat acidic, alcohol is somewhat acidic. You could use, let's take a look at antacids. Well, that's going to neutralize the acidic environment of the stomach. H2 blockers block histamine receptors. Remember back then, histamine increases, so does it increase in hydrogen ion concentrations. So if you block the histamine, you're going to block the production of hydrogen ions, lower the pH, or not lower the pH, raise the pH, making it less acidic. Also, the proton pump inhibitors that we saw in the parietal cells, if those are blocked, so the hydrogen potassium pump is blocked, then we don't have hydrogen leaving the parietal cells, we make less hydrochloric acids. So these are ways you can treat GERD. Basically, the bottom line is we're trying to make less acidic environment for the esophagus. Okay. Go with something that makes you vomiting. Emesis would just be the pressure building up in the stomach and forcing food back out. You can read through that information. The small intestine. If you look at the small intestine here, it has 3 segments. Here's your pyloric sphincter, but then here's the duodenum, the jejunum, and then the ileum. And the ileums, and this is the ileocecal valve. This is the cecum right here. Ileum, cecum, ileocecal valve. Okay, so you look at it again, duodenum, jejunum, ileum, ileocecal valve, cecum, appendix, ascending colon, transverse colon, and descending colon. Now, the cells of the small intestine known as enterocytes enteral cells within the small intestine. They have various digestive functions, hormones, and mucus involved in absorption of various components that are necessary for the body. And the duodenum is the first part. It's retroperitoneal. Remember, it's outside that peritoneal cavity. The duodenal papilla is a place in that duodenum where the pancreatic duct and the bile duct come together, okay, and empty into the duodenum. The duodenal mucosa. Now, what's the duodenal submucosa? Remember, it goes serosa, muscularis externa, submucosa, mucosa. The duodenal submucosa has Brunner's glands, okay, that produce an alkaline mucus to protect the duodenum from acidic environment. So the Brunner's glands are duodenal glands, are in the submucosa of the duodenum, and they produce mucus to protect the duodenum from the acidic chine of the stomach. Okay. The ileocecal valve is a part that's going to allow the food to move from the ileum into the cecum part of the large intestine. It can't go backwards. Here's your muscularis externa. Now remember, they have these little circular folds, and the circular folds, basically, these folds are involved in both mucosa and submucosa of the small intestine, increase the surface area. The circular folds of both the mucosa and submucosa. They slow down the transit of chymes to the small intestine, so there's more time for absorption and digestion by the enterocytes. So the circular folds increase kind of the surface area and slow down the chyme, so there's more time for breaking down and absorption of the material as it moves through the duodenum. Okay. Now here again are the microvilli. Actually, these are the villi that are in the small intestine. If you notice in here, here's your internal endocrine cells, remember? The ones that produce gastrin. Now we have what they call intestinal crypts. See, there's your acinar part of that. You have the capillaries, okay? Now this is a simple columnar epithelium in the small intestine. So the epithelium of the small intestine is simple columnar. They have goblet cells for producing mucus. The lacteals are for absorption of fats. The capillaries are for absorption of other organic products. So the intestinal crypts, okay? If you back up here, intestinal crypts, the mucosa indentiform. So the villi of the mucosa. Now remember, the mucosa is the inner part of the histology of the alimentary canal. The mucosa is next to the lumen. You have these folds. The mucosa folds over to form this villi. Okay. Now, between the villi mucosa indents to form an intestinal crypt. Okay. So we have our intestinal crypts, the folds are the intestinal crypts. There. They fold over, but they fold in. Here's your intestinal crypts. And it's going to produce the Owl's glands with both internal endocrine cells and mucus secreting goblet cells. Now, the smallest folds, or the microvilli, are found in the plasma membrane of the enterocytes. Remember, the enterocyte are the cells. So if you look here, here is the this is the microvilli. Here is your villi. Okay, the folds of the small intestine. Within the villi, you have the enterocyte. That's the enterocyte. So each cell is an enterocyte. This is the mucosa folding over the floor of villi. Each cell, enterocyte within that, has brush borders with microvilli. Okay? Now, this is going to increase. Now, what is peristalsis? Peristalsis is actually the contraction to move the muscle, smooth muscle contraction, move food through the alimentary canal. It involves both the longitudinal and circular muscles. Okay. Segmentation is an intestinal churning, involves contraction only the circular layer of smooth muscle. So peristalsis is circular and longitudinal muscles, where segmentation is just the circular muscles. Okay. In the small intestine. Let's take a look here so I can see right here. Peristalsis involves both the contracting of the circular muscles and contracting of the longitudinal muscles. So food can move, gets squeezed together and then moves down, whereas segmentation is just contraction of the circular muscles. Okay. And appendicitis, inflammation of the appendix. We'll talk about that later on.